Okay, chapter 4, lesson 5 is an algorithm for curve sketching. So we're going to take a look at all the things we're doing in chapter 4. It's kind of a review chapter. Take a look at all the things we've been doing in chapter 4 and sort of bring them all together and use this knowledge to sketch curves. So it's coming to an end quick. Chapter 4 is coming to an end quick, and I'll do a couple of examples here, and then you guys will have your review assignment to finish off chapter 4. So basically, today's lesson starts with just a look at the course website and a discussion about why we're doing this and sort of what we're doing here. So I wanted to start with making sure that you guys read this intro over here. And we talked about developing skills and techniques for taking curve sketches and taking our functions. But we want to make sure we emphasize the fact that we should be able to do this algebraically. So that's working with the functions and what they give us and what information gives us that is presented with the original function. It reaches right back to grade 11 and grade 12 advanced functions, where when you have the original function, sometimes you can use it to determine the domain and the range and the intercepts and the roots, um, any symmetry that might exist or asymptotes, endpoint behavior, all alike to graph that function. Now remember, in advanced functions, you didn't do first derivatives and intervals of increase and decrease, and we didn't talk about second derivatives and inflection points. Okay, your teacher may have sort of indicated some of those terms and talked a little bit about that, but as an advanced function student, you didn't do that type of thing. We only have done that in calculus. So we want to make sure that we understand and give due credit to the advanced functions work right here. Okay, and then do what we can with our graph of our functions, and then do the first derivative and the second derivative tests, okay, and find these critical points and inflection points and increase and decrease intervals and concavity. Now, with all of this, that should help us really get a good sketch of the graph. But we also then need to understand when and if we bring in Desmos or any type of graphing technology. And I always want you to use Desmos or any type of graphing technology when you understand and work with functions. But I don't want you to use Desmos too early and sort of cheat. I want you to be able to make sure you can do this algebraically. Okay? And then when the time is right, you confirm your findings with Desmos. Or if you run into an issue, you check it in Desmos. And you use Desmos simply as the way it should be. And that's just a tool to support your graphs and your functions here. Okay. So I want to take a second and talk about the algorithm for curve sketching here. So our nice little step-by-step guide for curve sketching is this algorithm that you see for you on the course note in the steps here. So with the original function, we always can talk about the domain, okay, and the domain and the range, okay, of particular functions, making sure you know how to do that. How you find intercepts or zeros, including both the x-intercept and the y-intercept. Symmetry, if there's any symmetry, and that should be worked on. I know you talked about that in advanced functions. You should be able to look at a graph and see that there's some balance to it, or there's some symmetry to it. Two definitions of symmetry. Okay, and then the asymptotes and the work we did with asymptotes as well. So all of these, okay, all of these things, okay, can be, okay, okay, all of these are just from the function itself here, okay, the original function. Okay, the first derivative, okay, and the second derivative, obviously, okay, okay, helps us talk about things we saw in chapter 4, these critical points. Okay, are intervals of increase and decrease interval, the local extreme are the critical points here. And then the second derivative, okay, is the end of chapter 4. Okay, that's intervals of concavity or inflection points, okay, also called extreme points or critical points. And then curve sketching. Okay, curve sketching is what we'll do on this particular chapter here. So let's do one. Okay, let's start with this one here, and I have it open in Desmos, and as we finish it, okay, we'll take a look at this. All right, so what do we know about this type of function here, just right from the beginning? Okay, so what do we know? Okay, well, it's a quintic function, right? It's degree 5. Okay, that's degree n equals 5. Okay, so it's an odd degree, right? Okay, Okay, so the basic, okay, it operates, it looks like a cubic. Okay, so it has endpoints. Okay, so it has endpoints. Since a equals 3, the leading coefficient is 3, it's greater than 0. Okay, its endpoints, it's in these two quadrants here, so it's, okay, and it's in that area here, and that's because it's odd and it's degree 3. Now, what about some roots? When it's a degree 5 function, it can have as many as 5 roots. It has to have at least one root. Okay, and I'm going to take a look at, okay, maybe, okay, looking at some of these roots here. So our original function, okay, our roots. Oh, what else do we know? When we have our basic function, we know our domain, okay, of quintic functions, okay, and our range. Okay, so we have a basic idea what this looks like. Our roots are found, okay, by taking our original function and setting e equal to 0. Well, this original function can factor. We can factor it in x squared. I have 3, oh, I can factor it in x to the power 3. I have 3x squared minus 5. Okay, so I have some roots at 0. Okay, and that particular point is the origin, and I'd have some roots at x is plus or minus the square root of 5 over 3. Okay, that's a decimal approximation, but it looks like I've got, okay, okay, a triple root here. X to the power 3 is a triple root. Okay, so the triple root goes through the origin here and flattens through. It doesn't, okay, it operates like a cubic, so it's a triple root and it sort of goes through and bends. Double roots bounce, okay, or single roots go through. This happens to be a single root at positive root 5 over 3, okay, and okay, another single root at negative root 5 over 3. We don't have any even roots, okay, double roots or quadruple roots or whatever, and those ones bounce, okay, from below or above the function here. So we've got this situation. We'd have a point here, okay, and we'd have a point over in here, and we'd have a point over in here. So probably it looks like a little bit like that. I don't know exactly for sure. Okay, and we'll find out with the rest of this information here. Okay, so let's take a look at our first derivative. Okay, our first derivative, if I do my calculations correctly, all right, don't know why that's turning up in blue. Let's just get rid of that. Okay, so, and then we try to find a critical point. And we've done lots of this type of work. It's this squared. Okay, so I can factor out 15x squared. I've got x squared minus 1. Okay, and therefore 15x squared equals 0, or x equals 0, and x minus 1 equals 0, x squared equals 1, x would equal plus or minus 1. Okay, so I've got 3 critical points. These points, I'll do the calculations. Okay, we know this one, 0, 0. Okay, and we also have that negative 1. I just put in the negative 1 into my y value. I got that to be 2, and I left those calculations for you guys. When x equals 1, I've got a point at negative 2. So these are local mins and local maxes, and we further classify them by, okay, putting them into a sign chart. Let's do that now. So I've got actually a pretty large sign chart, okay, between negative 1 and then 0, and then from 0 to 1, and then from 1 and beyond. And I'm going to use this particular function right here, and that'll be and I need points at negative 2, I need a point at negative a half, I need a point between 0 and 1, so we can use a half here, and then I can use 2 here. Alright, I've got, okay, when x equals negative 2, I've got a positive, okay, and a positive, positive, so it's increasing in that interval. The next one I've got a negative a half, I've got a positive and a negative. Okay, that's negative, that's decreasing. When x equals a half, I've got a positive and a negative. Okay, the product of a positive and negative is a negative, and that's also decreasing. So that's the inflection point here when it's going from decreasing to decreasing. Okay, it's an inflection point. It looks like it's increasing. And finally, when x equals 2, I've got a situation where I've got positive and positive, and the product of two positives is a positive. So this is increasing. Okay, so if I got kind of what this looks like, maybe, kind of, sort of. Okay, so next up is my second derivative. And I'm going to go to the next slide and do the second derivative here. All right, so my second derivative is going to give us my inflection point, okay, my turning points here in my concavity situations here. So I've got, what's my second derivative here? Okay. Okay, so that's y double prime, and I have so 15 times 4 is 60, x to the power of 3, okay, and minus 30x. Okay, so when my second derivative is equal to 0, I've got 60 x to the power of 3 minus 30x equals 0. Okay, I can factor out a 30x, leaving me with 2x minus 1, I believe. Okay, so 32x squared minus 1 equals 0. Okay, so 30x equals 0. I still have this critical point. Now it's turning up as a root, okay, as a extreme point and as an inflection point here. That's what often happens with some very important points on my function. And I have two critical points, or sorry, inflection points here on this graph. So I've got quite a bit. I'm going to just do a final sign chart here for this. So I've got a sign chart when x is less than negative 1 over 2. I've got the next interval, then from 0 to 1 over root 2, and then 1 over root 2 and beyond here. Okay, and I have to do my second derivative. My second derivative is going to be 30x. I'm going to use this one. Okay, and I have points. I can go negative 1 here. I could go, I think I have to use, sorry, this is a half. Okay, that's half. I have to use negative a quarter here. I have to use positive a quarter. And I can use positive 1 here. Okay, when x is negative 1, what is the sign of this? That's it be a negative and a positive. Okay, and that product is a negative. It means it's concave down. Okay, this is a turning point. Here I've got a situation where I've got a negative. When x equals negative a quarter, I have the product of a negative and a negative. Okay, I'll leave the work for you guys. That's a positive, so it's concave up. Okay, I have here, I've got positive and a negative. Okay, that's a negative. That's concave down. Okay, and then over here I've got a positive and a positive. Okay, so when x equals 1, I'm putting 30 times 1 is positive, and then 1 squared times 2 is 2, take away 1 is another positive. The product of a positive and a positive, and that means it's concave. Okay, so I have to take all this information and try and get a good sketch of my graph. Okay, now that is sometimes a bit of a challenge. Okay, I think I've got, okay, if I remember correctly, I've got a point here and a point here, point here, and I think I've got sort of a situation that, okay, looks like this. Okay, and there's a symmetry. It is an odd function, right? The function had degree 5. Okay, so it's an odd function. Okay, and odd functions have symmetry, okay, about the origin. Okay, and there's this bend here. Okay, I've got local max, local min. I've got, okay, concave. There's a point of inflection, concave down, concave up, concave down, concave up. Okay, and that's kind of what it looks like. And I want to just take a look at, show you this in Desmos, see if we've got this kind of confirmed here. Okay, yeah, absolutely. There's our confirmed graph in Desmos. Okay, we're going to do 2 more. Okay, I'll save those for the next video. And these are much more challenging graphs. One's going to be a rational function, okay, and then the other one's going to be a very strange product of 2 functions here. So we're going to go and analyze those and take a look at these in Desmos. And we might very well incorporate Desmos a little bit quicker for these 2 unknown graphs. I want you to continue with this lesson in the course content online. There's more examples, and the textbook offers some more examples. But at the very least, we should be able to handle a function like this one here relatively easily. Okay, it involves a little bit of work when you have to show it algebraically, but it's something that you should be able to know how to do in this class. Okay, keep working in chapter 4, and good luck.